time for us to do some more practice involving the shell method. And of course, that means we want to be focusing on setting ourselves up for success. Because really the setup is the important part right now. And once we get there, the integration, that comes with practice. So think carefully about how to set problems up. If you're following along with the video, make frequent use of the pause button and say, how would I set this problem up? Pause and try it out yourself. The more you get practice, the sooner you start to say, oh, I see the patterns. I see how to mold the situation into one of the patterns that I've seen before. And the more that you do, the better you're going to get and the more powerful you're going to become as a problem solver and, yes, as a mathematician. You too can be a mathematician. Well, it's time for us to begin. So in our first problem, let R be the region bounded by the curves y equals x, that curve right there, y equals 2 minus x, that curve, and y equals x squared. So it's this shape, very conveniently given to us at the beginning. Now, there's two parts. Set up an integral, or possibly integrals, to find the volume when R is rotated around the x-axis using the shell method. Then part B, set up again integral, possibly integrals, to find the volume when R is rotated around the x-axis using the washer method. Okay, so in both cases, we're actually looking for the same quantity. Now, a nice thing about this problem, we only have to set it up. We don't actually have to see what the answer is. So, kind of a little sad we don't get to do the problem right to the end, but we'll live with it. We'll live with it. Now, let's think about what we need to know. We know we're rotating around the x-axis in both cases. Okay, that's good. We should probably spend some time identifying intersection points. Now, some of the intersection points are a little bit easier to spot than others. For instance, down here, where x squared and x intersect. Well, that's the origin. Okay, not really too much thought going to that. How about where does x and 2 minus x, where do they intersect? Well, we would need to have x equal 2 minus x, or that would really say 2x equals 2, which means x has to equal 1. So this is at the point 1, 1. Now, this one, that one might be the most work. Where does x squared and 2 minus x intersect? Well, we need to have x squared equals 2 minus x, which is the same as x squared plus x minus 2 should be 0. Well, that's a quadratic. We can solve that. So let's see. Probably it should factor. That seems to be the kind of rule of thumb. Oftentimes things factor. In real life, they don't factor. But also in real life, calculators exist. So I've been told by my students that calculators exist. So let's see. X. We want two things that multiply to minus 2 add to positive 1. I think it would be plus 2 and minus 1. So does that work? X squared minus x plus 2x, that's plus x minus, yeah, that works. So we get two candidates, negative 2 and positive 1. Well, clearly we're looking for a negative x value, so that would say that our coordinate here is negative 2 comma, square negative 2, you get 4. But you could also take 2, subtract negative 2, which would also be 4, so that's good. So now we have our basic setup. So let's start with part A. We're trying to set up an integral that we're going to go around the x-axis and we're going to use the shell method. So we first have to make a decision. Are we integrating with respect to x or with respect to y? And what we mean by that is how are we slicing? So this problem really is going to ask us to do it in two different ways. So let's think about how we could figure that out. We know we're going here around the x-axis. We want to get shells. So that says I want to have a shell. So I want to go in this sort of pattern here. That's how I would get a shell. So that says, what kind of slice am I looking for? A horizontal slice. So part A is a horizontal slice. And when we're talking a horizontal slice, what that really means is that we're going to integrate with respect to y. So in other words, our slices are, we fix the value for y. So that's our part A. So we take a look at it for a second and say, what happens to our slices? So we can visualize, I'm sort of drawing some here. Say, okay, so far so good. And then something like, something happens to our slices. Indeed, something kind of frustrating happens. Notice there's a transition in behavior. Below 1, down here, we see that as we look at our slices, we go back and forth between the curves y equals x squared and y equals x. Above 1, we go back and forth between the curves y equals x squared and y equals 2 minus x. Now what does that mean? Well, what it means is there's a transition in the bounding curves. So we're transitioning between the curves 2 minus x and x at some point. Now, every time that there's a transition, that means we have to split our integral because we have to account for the fact that there's two different behaviors. So when we do part A, we're going to have to do two integrals. So one for each type of behavior. All right. So, well, it is what it is, right? Well, let's set up part A. Now, for part A, it's the shell method. So how does the shell method work? We'll do a quick reminder. We're adding up start to finish. We have 2 pi. We have our radius, our height, and we have our thickness. So that's what we're going to do. Now, how does that translate for us? So for part A, let's think about what we have. We have to think about our thickness. Well, for us, because we're integrating with respect to y, that's going to be our dy. So that helps us a lot. Now, one of the things we should do, since we're integrating with respect to y, is we really want to rewrite all the curves not just as y as a function of x, but as x as a function of y. So, for example, y equals x really can be the same as x equals y. Well, that one's not too surprising. Y equals 2 minus x, well, we can swap the roles here of x and y. And what do you get? Well, you add x, subtract y, and you get x equals 2 minus y. Wow, that's actually pretty easy so far. Y equals x squared? Right? Take the square root, and you get x equals square root of y. Right? Right? Oh, careful, careful. Why is that not right? Well, think of the picture. Look at what we can say about the x values over here. These are negative x values. So x equals the positive square root of y would be the part of the parabola on the right-hand side, which we're not using. So we actually need x equals negative square root of y. So we have to kind of keep track and make sure we're capturing everything that we need to capture. Okay, so now let's go through piece by piece. So let's suppose we start at the bottom. We might as well work our way up. We say, all right, where are we going from? Well, low value for y is at the very bottom, 0, up to the transition point. So we're going to go 0 to 1. 2 pi. Now, what's our radius? Well, our radius is how far we are across the horizontal length, because we're horizontal slicing. Okay, so that would be from where? Well, we're going to go from the right-hand side, says that our x value is y. The left-hand side, it's minus y. So it's going to be our, whoops, I got that wrong. Got to be careful here. That's not the radius. That's the height. The radius is what? Radius is how far down to where you're spin. So how far are we from where we're spinning? The answer is y. It's the height. That's the part that's here. Sorry about that. Gotta pay. Sometimes when you turn, it throws you off your game a little bit. So, okay. So anyways, y minus root y becomes y plus root y. Good. dy. All right. That's going to take care of the part underneath. Now we've got to do the second part. So plus integral from y equals 1 up to y equals 4. So this top side. So 1 up to 4. 2 pi is still there. Our radius, well, again, it's how far to where you spin. Still y. All right. And now our height, well, that's the distance between the two sides. So we're going to go from 2 minus y out to minus root y. So it's going to be 2 minus y minus root y, which is really going to become a plus root y, and dy. And there's our answer for part A. Okay, good. Halfway there. Now there's nothing too surprising, but it would take time to do the integral. So instead, we now transition to part B. Okay, so what's part B? So we want to now find it using the washer method. Well, that says when I'm spinning, I really want to spin kind of this way. So I don't want to make a cylinder. I want to spin to have a shape that stays flat. So that says, hey, I want to now do vertical slicing. So for part B, what's going to happen is we're going to do vertical slicing. Now, what does that mean? Well, it really means we're going to integrate with respect to x. So we're going to move with x, see? Because vertical slices are, we're going to fix x. And so, now, how many integrals do we need? Well, let's do the same thing we did before. Let's think about what's happening with our vertical slices. So what we're looking for is any time we have a change in a curve. Does that ever happen? Yes, it does. See, from 0 to 1, we have nice flat curves. But from -2 to 0, one of our curves is the parabola. Not so flat, which means it's a different curve. Different curve, that says we've got to really split into two parts. Okay, so two integrals. All right, well, maybe it's not so surprising. Well, what do we need? So what's our basic formula? So volume is adding up a to b in the washer method. We have pi, and then we have the big radius squared minus the little radius squared, and then you have your thickness. All right, that's our basic formula. Compacted a little bit. Okay, so what do we do in our case? All right, well, let's go from left to right. So we say, all right, where do we start? Well, our lowest value is over at -2. So we're going to have -2, and that's going to go all the way up to 0. 0 is that transition behavior. So from -2 to 0, we have consistent bounding curves. So -2 up to 0, and then we're going to have our pi, and now we have to say, well, what? Well, our outer radius is from the top curve down to where we spin. So our top curve is the 2 minus x. Notice that here we're going to integrate with respect to x. So I really want everything involved to be a function of x. So 2 minus x squared. subtract x squared squared. So subtract, I'll leave it as x squared squared and dx. Plus, and now we're going to go from 0 and we're going to go to 1 because that's where we stop. 0 to 1 pi, and now what's the top? It's still 2 minus x. So 2 minus x squared, that's our outer radius. Subtract, what's the bottom? Well, it's y equals x. So subtract x squared dx. And that's the setup for part B. And there you go. Those are the two different possible variations, parts A and parts B. And if you were to work them out, what would be true? We're not going to, but what would be true? And the answer is they'd be the same value. Not so obvious when you've written it in this form, but, well, it has to be true. It has to be true. Amazing. Amazing. All right, good. So this is more about setting things up, and it's nice to understand, okay, am I integrating with respect to x? Am I integrating with respect to y? Am I doing horizontal slicing? Am I doing vertical slicing? When you can start to get that intuition for what you're doing, it really starts helping you understand how to set things up, and there's a lot of power involved in that. All right, good. Well, that was kind of a long problem, so we deserve a little bit of a cool down, right? Let's have a fun problem. Now, of course, many of our problems are fun, and some of our funnest problems can be long. Well, let's see what this one does. Find the value of B so that the volume, which results from spinning the region R from x equals 0 to x equals b, and from y equals 0 to y equals e to the minus x squared around the y-axis, has volume half pi. Let's try to get a sketch of what our region here looks like. So, all right, we draw ourselves some axes here. And we're going from x equals 0, okay, so that's x equals 0, to x equals b. Well, we don't know what b is. We have to find it. And now we're going to go from y equals 0, which is here, to y equals e to the minus x squared. Well, that actually is a kind of a famous curve. It's called the bell curve. And if you were to sketch the whole thing, the reason it's called the bell curve is it kind of vaguely resembles a bell. But for now, let's just say that it looks something like that. So here's the curve, y equals e to the minus x squared. And now we have our region. So there's our region R. Okay, so this is our region R. And we're going to spin this around the y-axis. So we're spinning that way. And what are we trying to find? Well, we're trying to find what our value for B is. You see, we already have our volume. It's been given to us. Our volume is a half pi. So what we have to do is start thinking about, okay, how do we figure out what B should become, the correct value? Well, how would we compute the volume here? Well, let's think about it. Let's reason over how we would approach computing the volume. If I were given the problem to compute the volume, I would say, well, since I'm given y as a function of x, a reasonable thing would be to integrate with respect to x, which means to do a nice vertical slice, so that when I spin, the shape that I see when I spin is a shell. So let's try using the shell method. It's a reasonable thing to say, if you're given variables, y is a function of x, start by trying to integrate with respect to x first. Only if you can't, then do we integrate with respect to y. So let's see what we have. We have 1/2 pi is the volume, which is a shell method. So start to stop. Then we're going to have 2 pi, our radius, our height, and our thickness. All right. Now, some of these pieces are pretty easy to figure out what they should be. So for instance, our thickness, that's pretty much given to us because we know how we're slicing. That's going to be our dx, which also tells us about what our bound should be. So we're going to start at 0, and we're going to go, well, to somewhere. We're going to go to b. We don't know what b is yet. But, okay, that's what we're trying to figure out. All right, how about our radius? Well, that's our distance to where we spin around. So we're going from x over to 0. So the radius is x. How about the height? So the height is this length up and down. So we're going from 0 up to that curve. So that would be e to the minus x squared. All right, well, that's something. So what do we have? We have integral 0 up to b of 2 pi x e to the minus x squared dx. All right, good. So now we just have to figure out what the right value for b should be. Which means we should probably make progress in doing the integral. So how can we integrate this? Now, if we just had e to the negative x squared, we'd be in trouble. E to the negative x squared is just not pleasant to integrate. But we have a little bit extra in the front. Maybe that little bit extra is just enough. And if you look at this, and you don't have to look too long, you start to say, if I think of the derivative of x squared, that would give me 2x. Okay, so here's what we can do. Let's do a substitution. So our substitution will let u equal x squared. Then, in fact, let's go ahead and throw the negative in there. U equals negative x squared. Why not? And then what would du be? It would be negative 2x dx. They might say, well, wait a second, there's no negative there. Okay, well, we'll just do a little doop, doop. Okay, there we go. Now there's a negative. Negative du equals 2x dx. So what does this become? Integral. So e to the minus x squared becomes e to the u. 2x dx becomes a minus du. Now, that's the 2, the x, the dx. We've handled e to the minus x squared. We need to handle the pi. Well, pi is a constant, so that's easy enough. Now the bounds. So 0, negative 0 squared is still 0. And then plug in b, negative b squared. Well, all right, just leave it as it is. Perfectly fine to leave it as negative b squared. Now, this is an integral we can do. So let's integrate. This would be minus pi e to the u evaluated from 0 to negative b squared. Or that's minus pi times e to the minus b squared minus e to 0, which is 1. Now, I might pause for a second here and say, am I allowed to have this in this order? Because clearly negative b squared should be smaller than 0. Am I allowed to evaluate a smaller number on top and a lower number on the bottom? And the answer is, yeah, it's perfectly fine. The way that it's set up, it will automatically correct itself. So if you wanted to switch, you could. And if you'd switch, what would happen? Well, you would just get rid of that negative sign. In the end, things work out as you would expect them to. Okay, so let's remember where we're at. This is equal to, working our way back, 1/2 pi. Okay, now we're ready to sort of clean up and get our answer, which is good because we like to get an answer. So let's see, what can we do? Well, we can cancel some pi's. Woohoo! That's nice. And if we multiply the minus through, we are to the point where we have minus minus 1 makes 1 minus e to the minus b squared, right, because the minus goes through, equals a half. Well, just swap those two. That tells us that e to the minus b squared has to be equal to a half. All right, well, that's something. Now, we need to get the b by itself. So, how can we do that? Well, we can bring the b squared out of the exponent. And then we can, how do we do that? Well, that's natural log. Actually, there's a little trick here. I just want to point something out. We can be a little bit sneaky here. It's not so sneaky. Notice that that's e to the minus b squared. Let's shoot over here because we have lots of space in this corner. E to the minus b squared is the same as 1 over e to the b squared, right? Because a negative just means a 1 over equals 1 over 2. So if I flip both sides, that says e to the b squared equals 2. Now I got rid of that negative sign. And I got rid of it by flipping both sides. Take a natural log, b squared equals natural log of 2, and we're almost home. What's left? I want to get rid of the square. Well, I need to find the value of b. It should be positive, right? So I really want to go that way. Now, you'll notice it actually doesn't matter whether we choose positive or negative. It turns out both will work because there's symmetry. If I were to sketch the curve on the other side, it would be exactly symmetrical. So plus or minus would give the same thing. But we'll assume that they really meant to say the positive one. And therefore, our answer is b should be the square root of natural log 2. Good. And that's what we're after. That's the answer. All right. Well, probably not what we would have guessed at the beginning, but we don't want to guess. We want to be methodical and start working on a problem. Okay, what do we do? What do we change? Well, how do we figure out what to do to proceed and make progress? So that's good. We made good progress on that one. Beautiful, beautiful answer. All right, well, let's try another problem. So let's see what the next problem is going to have for us. Given that f of x is greater than or equal to 0, and then when the region 0 less than or equal to x less than or equal to 4, and 0 less than or equal to y less than or equal to f of x is spun around the x-axis, the volume is 22 pi, and when the same region is spun around the y-axis, the volume is 14 pi. Determine the volume when the region, same region, 0 less than or equal to x less than or equal to 4, at least the same x values, but for y, a little bit different. 3x plus 2f of x. Okay, so it's sort of a different shape. And then we're going to spin that around the x-axis. So, a little bit to digest here. So, there's sort of, let's start with what we know. Well, we definitely don't know f of x, but let's pretend like we can say we did. And say, well, we're going from 0 up to 4, and there's something here. Okay, so here's the y equals f of x, some strange unknown shape. So this is our initial region R. All right, so there we go. And our picture is at least somewhat accurate in the following sense, namely, we know f of x is greater than or equal to 0. So it's a reasonable picture. So let's start by figuring out what these statements mean. When we take this and we spin around the x-axis, the volume is 22 pi. So let's spin around the x-axis. If we were going to spin this around the x-axis, what method would we need to use? Well, because we don't know anything about the function, we always are going to have to do our slices up and down. They're always going to be vertical slices. So when I'm spinning here around the x-axis, the shape I'm going to form from spinning is going to have to be a disk. So I'm going to form these little circles. All right, so we have that 22 pi is equal to, well, the volume around the x-axis, which is, we're going to go from adding up, which means integration, start to finish, those are the bounds, and then we're going to use our disk method, pi times our radius squared times our thickness. Now in our case, the radius is up to the function. So our bounds are 0 to 4, and then we have our pi f of x squared dx. Okay, good. So now we have some information. We know how to compute pi times f of x squared dx. Okay, so that's sort of that first sentence, but we keep going. When we spin that same region around the y-axis, the volume is 14 pi. So now we're going around the y-axis. Okay, what happens there? Well, we have our same vertical slicing up, down. So when we spin, what are we forming? Our shape is a shell. So we have that 14 pi, which is the volume when we spin around the y-axis, is equal to, okay, adding up, start to finish, 2 pi. Then we have our radius, our height, and our thickness. So that would be integral 0 to 4, because that's where we go from, x equals 0 to x equals 4, our 2 pi. Our radius is how far a slice is from the y-axis. That would be x. Our height is f of x, and our thickness is dx. See, be careful here, because radius, you'll notice they represent different things. Here, when we talked about the disk method, radius really was about the height of the function. Whereas when we talked about the shell method, radius was how far from where you're spinning. Well, in both cases we were correct. It just depended on context. So use context to make sure you understand what things represent. Okay, so good. We've taken the information that we had and we've used our formulas to say, oh, this volume, which is 22 pi, really corresponds to this integral. And this other volume, which is 14 pi, really corresponds to that integral. All right, well now the question becomes, how do we use those integrals? So let's figure out what we're looking for. So the question says, determine the volume, all right, so we're doing a volume, when this new region, now our new region is not the same region. So what's happening? Well, we're making the f of x taller, we're doubling it, and then we're also adding this 3x here. So it's going to be, going something like that. So it's a lot taller up. Okay, so here's our new region R, where we have y equals 3x plus 2 f of x. All right, so we're going to spin our new region here. Where? Well, we're going to spin it around the x-axis. Now, you might say, well, all right, interesting. Now, if we think about what we're doing here, we've already spun around the x-axis in our old region, and we used the disk method. So you're like, well, why do we need to have this extra piece of information that came from the shell method? That seems redundant. Well, let's not make too many assumptions about what we do and don't need. Let's let the problem guide us and see what we end up using. So, same as before, we're going to spin, and when we spin, we're going to form our little disk. So, our volume that we're after is what? Well, we have our same basic setup. So we'll just go ahead and go through here. Start to finish, 0 to 4. All right, that's no problem. Pi, our radius is our new function. So that would be 3x plus 2 f of x, quantity squared. And then our thickness is dx. So our goal now is to figure out what is this integral. So let's start working with it. So we'll square this out. That's oftentimes a good thing to do whenever you're working with a problem. So we have integral from 0 to 4, square 3x, that would give us 9 pi x squared. Now, the cross terms. So, see, like the 9 pi x squared, that's a squared. Then there's the pi. Now, the cross terms would be 2 times a times b. So 2 times 3 times 2 would be 12. So 12, then there's a pi, don't forget that. And then there's an x, f of x, plus, square the last term. That would be 4 f of x squared, don't forget the pi, plus 4 pi f of x and squared. All right, good, dx. All right, good. Now, let's see what we can do. Well, we want to somehow use what we know. We say, wait, look, there's an f of x squared on the last piece. We know how to integrate f of x squared. So we say, aha, if I break this last piece off, pulling out the 4, I've got something I can work with. Perfect. And then we say, oh, look, there's an x, f of x in here. We can use that. All right, good, progress. So let's break this up into small pieces. Now the first piece doesn't involve f of x at all. No problem, we can handle that. So what does that become? Well, we'll say, I'm going to write it, because I can see the x squared, I can anticipate what's going to happen. When we integrate x squared, we end up with x cubed. So I'm going to actually do the following. I'm going to break it up as 3 pi integral 0 to 4 of 3x squared dx. Okay, I'm just making it so that what I integrate is easy. Now the next piece looks most like that. The difference is here there's a 2, there's a 12. Well, we're off by a factor of 6, so we'll pull out a 6, so plus 6 integral 0 to 4 of 2 pi x f of x dx. The last piece almost is exactly that, except the factor of 4. Okay, we can fix that. So plus, pull out the 4 integral 0 to 4 of pi f of x squared dx. All right, now what do we have? Well, we have the following. The 2 pi x f of x dx becomes 14 pi. Okay, so that's 14 pi. Pi f of x squared dx, that integral becomes 22 pi. All right, wow, we can get some big numbers here. And then this integral, we can integrate it, that's x cubed from 0 to 4. Well, okay, 4 cubed. 4 times 4 is 16, times another 4 makes it 64. So that's 64 times 3 pi. So 3 pi times 64. All right, well, now the time for us to finish it. Let's do it. Let's get an answer. We always want answers. Answers are great. 3 times 64, that would be 180 plus a dozen more. 3 times 4 is 12. So that's 192 pi. 6 times 14. Well, 6 times 10 is 60. 6 times 4, 24. So that would be 84. All right, so 84 pi. Good. 4 times 22. Well, that would be what? Well, 4 times 22, 88. So 88 pi. Now, we've got to be careful here. This is a great time to use a calculator. The good news is it's going to have something pi. Now, if you didn't have a calculator, probably the easiest thing is to say, Well, 192 plus 88, that's not so bad. See, if you add 8, that gets you to 200, and then add 80 more, that gets you to 280. So now 280 add 84 gets you to where? Well, it would get you to 364 pi. And there you go. That's the answer. All right, interesting answer. Kind of, maybe not what you would have expected. Almost you want it for 365, right? But 364, we'll take it. A nice answer. And it's nice that we can actually find the answer. And it doesn't seem so obvious how the shell method comes into play. But it shows up because, of course, you get this x, f of x term showing up. In some sense, you might think by the end here, it's like, oh, if I see x, f of x, maybe I should start thinking of shell method. Maybe you should. We do that a lot, at least in these problems. Of course, if you see somebody else's problems, who knows what you might see there. But at least in these problems, we get to have some fun. Okay, well, let's do another problem. All right. Find the volume when the region where x goes from 0 to 8 and y goes from 0 to the square root of x squared plus 10x is spun around the line x equals -5. So it's all laid out for us right here. We have a picture. Isn't it great? It's like they really want us to understand what's going on. So we start thinking about, okay, what should we do? Well, let's just take it at face value and say, well, the problem here is our region gives y as a function of x. So let's take advantage of that, and let's start by looking at doing a vertical slicing, which really corresponds to saying let's integrate with respect to x. When we spin that vertical slice, what we'll see is we'll see a little bit of a cylinder or a shell. So we're going to think about shell method. So here we go. Shell method. What do we have? Well, the volume comes from adding up from where you start to where you finish. Then we have 2 pi, our radius, our height, and of course our thickness. And now we just have to start figuring out what are all these pieces and put everything together. So let's start with the various things. We know the thickness, vertical slicing, really says we're integrating with respect to x. Okay, we know we're integrating with respect to x. So that says our bounds should be x bounds. So as we take our vertical slicing, where do we start and stop for x? Well, we can use the picture, 0 to 8, but we also see it right there, 0 to 8. All right, so we're going from 0 to 8. So start at 0 and end at 8. Good. All right, so now we have our bounds. We have our thickness. We're making progress. How about our radius? What would that be? Well, it's from our slice to where we spin. So this would be our radius. So I'm at x here. I want to get to -5. How far is x from -5? Well, you take the right, subtract the left. X subtract -5 would make it x plus 5. How about the height? Well, the height is this length. How far up and down do we go? So that's from 0 up to the curve square root of x squared plus 10x. So that would be the square root of x squared plus 10x. All right, good. All our pieces are in place. So let's see what we can say. This is going to be the integral 0 up to 8, 2 pi times x plus 5 times x squared plus 10x, the square root of that. Well, maybe we should write that in a very calculus-y way. Now, the reason I say a calculus-y way is a square root is not the most convenient way to write things. We prefer to write it as to the half power. That's a more calculus-y way to write it because that helps set us up for things such as, power rule. Adding 1 to the exponent, dividing by the new exponent, and things like that. So we start to say, what can we do? What can we do? Well, that's a great question. What can we do? We can start to think, here, it's not going to be easy to simplify the square root of x squared plus 10x. And definitely, this is not one of our basic functions that we just automatically know. Something else has to be done. There's no trig. There's not really any algebra that I can see. So I'm thinking substitution. Well, is there a good candidate for substitution? If we think back to substitution, sort of the mantra of substitution is to remember that substitution is an inside job. All right, well, is there a function that's on the inside? Okay, well, that's a good question. And there's a good candidate. This x squared plus 10x, that's on the inside. Let's try that. And let's just see what happens if we start there. So if we let u equal x squared plus 10x, what would du become? Well, the derivative of x squared plus 10x would be 2x plus 10. Okay, now the question is, do we have a 2x plus 10? Well, notice I have 2 times x plus 5. And if you multiply that through, that is 2x plus 10. Perfect. Exactly what we needed. Ha! 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 Yes, good. We can make progress. Oh, this is wonderful. Okay, let's see what that's going to give us. All right, so integral, let's do the bounds. So the old bound of 0, plug 0 in. 0 squared plus 10 times 0, well, that's 0. Okay, how about this one? 8 squared plus 10 times 8. Ooh, that one's a little trickier. 8 squared is 64, and 10 times 8 is 80. 64 plus 80, also known as 144. Now you might be thinking, gross? Exactly. 144 is also known as a gross, 12 squared. And, okay, that's a different story. But all right, back to our regularly scheduled problem. Now, the pi is going to be pi. Not much to do there. The 2 times x plus 5 times the dx is going to become our du. The x squared plus 10x to the 1/2 becomes u to the 1/2. All right, well, that's not so bad. So what do we end up with? That's pi. Add 1 here, so that would be u to the 3/2. And then you have to divide by the new power, which really means multiply by 2/3, from 0 to 144. All right, well, okay. Well, the nice thing is you plug in 0, you get 0. So this is pi times 2/3 times 144 to the 3/2. And we would probably be okay if we left it like that. Now, let's see if we can maybe just squeeze a little bit more out of that. Because I have hope that maybe we can squeeze a little bit more out. Now, let's think about 144 to the 3/2. There's really two things going on. I'm going to cube it, and then I'm going to square root it. Or maybe I can square root it and then cube it. Now, oftentimes it's easier to go small and then big. So 144, is that a nice number? In other words, is it a square? When I take a square, do I get something nice? Well, 144 is 12 squared. So you could say, hey, this is really 2/3 times pi, don't forget the pi, times the square root of 144 is 12, so times 12 cubed. Okay, well, that's something. Now, what can we do with that? Well, we're really starting to get close to the end here of things we can do in our head. So 12, all right, let's write this out. This is 2/3 times pi times 12 times 12 times 12. Well, 3 can go into a 12, leaving us with a 4. So we really have 2 times 4 is 8 pi. And then 12 times 12, we've already done that, is 144. So we're almost there. Okay, 8 times 144. All right, well, this is really a good chance to use your calculator. 8 times 100 is 800. 8 times 40 is 320. 8 times 4 is 32. And we add those up, and we get a pi on the end. Then there's a 2. Then there's a 5. And 8 plus 3 makes 11. So 1,152 pi. There we go. Final answer. Beautiful. Good. Good. But of course, we could have probably left it here and be okay. Or use a calculator. It's not such a terrible thing to use a calculator. I mean, that's one of our goals, is to say, look, the calculators are great for doing the menial computations. We're here to do the interesting things, like setting things up. Calculators can't set things up. Not yet. And I hope they don't get to that point, because I feel like I'll be out of a job if a calculator can set problems up and also solve them. So that's why it's good to know how to set things up. That makes you better than a calculator. And, well, of course you are. You're much better than a calculator. Okay, well, good. Good problem. Okay, well, let's do another problem. All right. Set up an integral to find the volume when our region where x goes from 0 to 1 and negative 2x to y to 1 over 1 plus x to the fourth plus 3x to the fourth minus 2x is spun around the y-axis. So it's kind of a weird-looking shape here. And it's not so clear what this shape will do. All right, well, what can we do? Well, let's just think about what we have. Now, from here, we definitely don't want to do any horizontal slicing. Horizontal slicing would be so dangerous here, because can you imagine doing a horizontal slice where you're like, well, a piece here, and then you have to do another piece over there, trying to find the inverse of this? Forget it. Forget it. Hopeless. Hopeless. So we're having to do vertical slicing. So, well, that means we're going to go up and down. All right. And so when we spin, we're going to form our little tiny cylinders or our little tiny shells. Okay, so definitely we're in our shell method mindset. No problem. We're okay with that. So, what do we have? Well, shell method says what? If we're looking for our volume is adding up, which means integration, from our start to our stop, our 2 pi, then we have our pieces. There's our radius, there's our height, and of course there's our thickness. Now, because we're going to be slicing up and down, our thickness, our little thin part, well, that's going to correspond to a small change in x. So our thickness is a dx. Okay, so we're going to integrate with respect to x. We know we're looking for x bounds. So x goes from 0 to 1. Okay, so we're going from 0 up to 1. So far, so good. Our radius is how far we are from where we spin. Well, we're going around the y-axis, which really corresponds to x equals 0. So our distance would be x. Now our height. Okay, so that's how far up and down we go. So what is our height? Well, you're going to take our high minus low. High value, subtract low value. So what's the high value? Well, it's the top function. So that's 1 over 1 plus x to the fourth plus 3x to the fourth, subtract 2x. Okay, that's the high minus the low. So subtract minus 2x. All right, that's our height. Now, let's pause for a second and make a quick observation. Do you notice anything about our height? Well, notice these minus 2x's here are going to end up canceling. So these two pieces, because they're the same, they end up not mattering. What's happening, what's going on is they're causing it to shift up and down, but because you're shifting the bottom just as much as you shift the top, the height ultimately doesn't matter. These things right here, I could have put any function I want. So I could come up with some crazy function f of x and some other crazy function f of x to make you super, super nervous, but it wouldn't matter, even if I didn't know what f of x was, because they end up canceling out. So it is possible that sometimes things that look like, they're like, this is going to be terrible, it's going to make the problem impossible, then you look at it, it's like, oh, wait a second, that doesn't matter at all. That's a red herring, misdirection. So it can happen, sometimes deliberately. Okay, so what do we have here? Well, let's see what we have. So this would become integral 0 to 1. And let's see. Well, there's a pi. I'll put the pi all the way out in front. So then there's a 2x. And then I'm going to multiply the 2x through. So I have a 2x over 1 plus x to the fourth. And then here I'll have a 2 times x times 3x to the fourth, which would be plus 6x to the fifth. All right, good. Now, one of these integrals is pretty straightforward, and the other one will need a little bit of work, but not too much. So let's break this up into two pieces. So we're going to have our pi, and 0 to 1, 2x over 1 plus x to the fourth dx. This is one of the nice things about integration, is you say, look, if you have things being added and subtracted, you can either put them together or you can take them apart. Because it might be like, hey, when you put things together, they combine in a nice way, and then your problem is easier. But it can also be the case that, hey, really to do the problem, in this part, I should use method A, in this other part, I should use method B, and then at the end of the day, it's like, hey, I should separate them because I'm doing two different things on the two different sides. No problem. That's perfectly fine to do. Now, which one is the easy one that sort of jumps out and says, aha, I see what that is right away? For me, it's the second piece. You see, because it's just a power of x, that's actually pretty straightforward. And indeed, look at how nice it is. When we integrate, we would add 1 to the exponent, which would make it x to the 6, divide by 6. So that would say that at the end, this is x to the 6 from 0 to 1. Well, that's an easy evaluation. It's 1 to the 6, subtract 0 to the 6, which would say that the integral is simply 1. Then don't forget the pi. Okay, so that's going to handle that second part. Good. 2x over 1 plus x to the fourth. That one maybe not so trivial. So how do we handle that? Well, let's think. What can we do? What can we do? Well, whenever I see some things like 1 plus something squared downstairs in the denominator, I always start to think, oh, is there an arctangent involved? I always hope for arctangent, because I love arctangent. It's such a great thing. So I'm starting to suspect maybe there's an arctangent involved. Now, at the beginning, I don't see an obvious way to integrate this. And so I'm starting to think, okay, there's no trig. All right, there's no trig identities. There's nothing algebra that pops out. So maybe a substitution. And, well, where can we look? Well, one thing we can do is we can say, you know, I see a 2x dx. Now, I know something where I take the derivative of it and I end up with the 2x dx. So that's very suggestive. That says you should try a substitution like x squared. Because if you do that, then you'll get that du is 2x dx. And you're like, okay, well, let's see what that would happen. So don't forget there's a pi. We'll come back and get that pi in a second. So we have an integral. Then the 2x dx would be our du over, now x to the fourth, well, that's x squared squared. So if u is x squared squared means you get 1 plus u squared. And now, how about our bounds? Well, we went from x equals 0, 0 squared is 0, so it's still 0, to x equals 1. 1 squared is still 1. So the bounds also are still from 0 to 1. Now we've changed. So we were x bounds before, we're u bounds now. But it just happens to be that they're the same. These things can happen. And now we're like, this is great. That's arctangent. We recognize arctangent. So we get arctangent of u and evaluated from 0 to 1. Well, that's really arctangent of 1. And then you subtract arctangent of 0. Now arctangent of 0 is 0, so the second term drops out. And arctangent of 1, well, that's the value we should know. That is pi fourths. Okay, so now let's put this all together. So what do we have? Well, we have the pi. Okay, don't forget about that. Then this integral, when we carried it out, is pi fourths plus the pi, and that integral turned out to be 1. So we end up with 1/4 pi squared plus pi. And there we go. That's it. That's the answer. Good. Okay. So, it maybe looked a little bit intimidating. Certainly the shape was kind of not so obvious that we could make good progress on it. But as we worked the problem, we see that things canceled in the right way, that as we were careful to keep track of the pieces that we had, it all came clean and beautiful. Something we could work with. Okay, so that's good. Good. Okay. Well, that brings us to our last problem. The end? Well, not our last problem ever, but the last problem for today. And this is one of those problems that I sort of stumbled across a couple of years ago. And I love this problem because it has nothing at all on the surface to do with things that we're talking about. But maybe you'll start to see it's like, oh, wait a second, I'm spotting certain patterns here. And now, as we start to spot those patterns, you're like, okay, now I can start to see them in other settings. And once you do that, power. All right. Well, let's think about it. So the problem says, find this easy-looking integral. Well, maybe not so easy-looking integral. So we're going to go 0 to 1. This is actually the picture here. So we're going from 0 to 1. So here's 0. Here's 1 of x minus the pith root. And yes, that does mean the pith root of 1 minus x to the pi, all that quantity squared. So you get this sort of strange shape. The question is, okay, what's the integral? Now, the reason this seems so strange is it's asking for, the way we look at it, an area. So we say to ourselves, well, how can we find this area? And what in the world at all does this have to do with volumes? There's no volume anywhere in this problem. You might say, well, there's pi's here. Those pi's are in the exponents. They are not normal pi's. It's just weird. It's really weird. What's going on here? Why are you doing this to us, Steve? That might be what you're saying. And my reaction is like, this is going to be good. Okay, so let's dig into it. All right, so as we get going here, we say to ourselves, well, I see a square. We've done this a couple of times. See a square, that means square it. So let's do it. So we have the integral 0 to 1, and we have x squared, then the cross terms, minus 2x times this sort of strange looking thing, the pith root of 1 minus x to the pi, and then plus, we take the pith root of 1 minus x to the pi, quantity squared, and we're going to do that dx. Okay, now, here's where things get sort of like, huh. And so I'm going to be honest with you from this point on. If the following step says, I would not have guessed this step, you're okay, because the next thing we're going to do is not so obvious. But when you see it, you're like, wow, that's so cool. That's so cool. Okay, so let's think about how we can connect to what we've been talking about. We've been talking about volumes of revolution. And so when we see things that look like, oh, 2x times a function, it feels like a shell method. When we see things that look like oh, function squared, that feels like a washer method. So let's think about this function. This is kind of a strange function. So we're going to do a little bit of work on the side for a moment here. So suppose I look at this function, y equals the pith root of 1 minus x to the pi. Now, you're probably not recognizing what this looks like, but suppose we wanted to get a feel for it. Now, one thing we can do, when we say the pith root, that really means 1 minus x to the pi to the power 1 over pi. If I raise both sides to the pith power, that makes it y to the pi equals 1 minus x to the pi. Well, rearrange. X to the pi plus y to the pi equals 1. Now, does this feel familiar? It kind of feels like a circle. Now, a circle would be x squared plus y squared equals 1. Well, it turns out you can use any power. It will only be a circle if x squared plus y squared equals 1. So you have to have the power of 2 to be a circle. But even if it's not a power of 2, it's circle-esque. In other words, it vaguely looks like a circle. So what we would end up seeing is something that looks kind of more, maybe a little bit more rounded here, a little bit more flatter towards the ends, something like that. Okay, so that's our curve, x to the pi plus y to the pi equals 1. Now, let's look at this piece right here. This looks a lot like if we were to do the shell method. Now, the shell method would say what? Well, shell method says if I see 2x f of x, well, that's like I took my slice and I spun around the y-axis. So if we take this shape and we go around the y-axis, what do we see? Well, the volume, if we work it out, would be integral from 0 to 1. You can see that when you have x equals 1 or y equals 1, you get 1 plus something equals 1, which means that you're actually at the intercepts here, 1 and 1. Okay, so going from 0 to 1 are 2 pi, and then x, and then the value of the function, which is the pith root of 1 minus x to the pi dx. Now, we do not know what that volume is, and we are not going to compute it. Okay, you're probably thinking like, ooh, we're going to find the volume. No, we're not going to. Okay, all right. Okay, hold on. This is where it gets good. Okay, now, function squared. That feels like disk method. So that would be if we went around the x-axis. But again, still the same function. So around the x-axis, what do we have? Well, we have that the volume, the volume here is equal to, well, integral start to finish, pi then the radius, which is the function, squared dx. Okay, so far you're probably thinking, yeah, where's the trick, Steve? What's true about these two volumes? Now, in one case, we spun around the y-axis. In the other case, we spun around the x-axis. What's going to be true about the two volumes that end up? Well, look at our shape. And this is the key idea. Do you notice anything about this shape? Now, you might say, well, Steve, the way you drew it, it seems symmetrical. But did you draw it accurately? Is it symmetrical? Now, this is the key thing. If you can believe the following, then everything else that follows is going to be great. I claim it is symmetrical. Now, what does that mean? That means that if you were to flip it or cross the line y equals x, the shape would not change. Why is that true? Look at the formula. X to the pi plus y to the pi equals 1. Swap y and x. What do you have? Y to the pi plus x to the pi equals 1. The same formula. Since the swapping doesn't change anything, the symmetry holds. So this shape is symmetrical around the line y equals x, which means if I take this symmetrical shape and I spin it around the y-axis, or I spin it around the x-axis, I'm going to form the same volume because I'm going to end up with the same resulting three-dimensional shape. So these two volumes are equal. So how does that help us? Cancel the pi's. Notice, what does that say? It says this integral right here on the end and this integral right there in the middle are the same except for the minus sign. So what does that do? Well, the minus sign, and this is the cool thing, it says we don't know what they are, but we do know that they are equal to each other. And since they're equal to each other, therefore, they must cancel out. And so they're gone. And so the part that was really hard about the integral, the thing that we couldn't do, they cancel each other out because we had the ability to say, oh, this can be interpreted as volumes. And in particular, that we can interpret these as two volumes which cancel. So even though we don't know individually what the values are, we know enough to say they're going to undo each other. Okay, so let's finish it up. So since those are gone, we get that this is equal to the integral 0 to 1 of x squared dx. Well, that's an integral we can do. So that's 1/3 x cubed from 0 to 1, and, well, leaving us with an answer of 1/3. All right, that's it. That finishes the whole problem. Now, was there anything special about pi? The answer is nothing at all. You could have used any number you like. So we could have done, pick your year you were born. Like me, okay, I'm not going to tell you what year I was born. There's a lot of gray here. But you could pick, your favorite number, e. Okay, the eth root of 1 minus x to the e. And it actually doesn't even have to be that. The key thing is any function at all, as long as the region is symmetric. That's all you need, is the symmetry so that you get cancellation. So this is kind of this fun idea that says, oh, hold on, can we start thinking about what things represent? And even if it doesn't necessarily start off by saying it's a volume, does it help me to think about it as a volume? When you can start seeing these things in unexpected places, it's a lot of fun. And I enjoy this problem. This is one of my favorite problems. And I have to, this is actually one I came up with. I'm sure other people have come up with similar problems before, but it's such a beautiful and unexpected application. A good time, good time. Thank you so much for being patient and sticking it all the way to the end. I hope that you enjoyed these problems, especially this last one, but all of them. And thank you for working on these problems and doing them, session in, session out. I know there's so much to do, but I know that as you keep working, you will get better and you're going to learn so much. And it's going to help you to see a beautiful world around you. All right. I hope you have a great day and see you again soon.